I would like to present our research about influence of irradiation of copper, indium, gallium diselenide thin films by electrons on photoluminescence spectra. In recent years, new materials for the photovoltaic are studied intensively. Copper, indium, gallium diselenide is one of the most prospective semiconductors for absorber layer of thin film solar cell. Besides the record convention efficiency among the thin film solar cells, this material has outstanding radiation hardness. Nevertheless, the physical reasons of such hardness are poorly explored. Further investigations of radiation defects generated by electron flux can clarify the nature of interesting defects in this material. The main technique we used in this study for analyzing of radiation effect is photoluminescence. Thin films were deposited on soda-lime glass substrates coated with molybdenum layer by the co-evaporation technique. And here you can see a cross-section and top view of these films. The elemental composition demonstrates copper deficiency to other metals and a slight selenium excess. Thin films were irradiated by electrons in liquid nitrogen baths. The photoluminescence measurements are performed at two stages. During the first stage, the films were measured at the liquid nitrogen bath straight after irradiation without rising the sample temperature. And during the second one, the films were warmed up to the room temperature and then were examined again. You can see samples excited by the wind laser in the liquid nitrogen. And the laser beam chopper along with locking amplifier were used to reduce the noise level. Irradiation reduced the photoluminescence intensity of the dominant band due to the formation of non-radiative defects, acting as drip traps. However, after the warming these films to the room temperature, the photoluminescence intensity of the dominant band increased significantly, what is probably caused by the annealing of some radiation defects. It can be seen at the logarithmic scale that the spectra contained 5 photoluminescence bands. Thin films were investigated in a wide range of excitation intensity, more than by 3 orders of magnitude. It can be seen that with excitation intensity rising, not only the intensity of the photoluminescent bands changes, but also the energy of these bands. This is due to the specific recombination mechanism. The main types of energy transitions which we can expect for such materials are presented on this slide. For example, band-to-band transition is a recombination of the free electrons from the conduction bands with the holes with the valence band. But at low temperature photoluminescence spectra, we can expect only 2 types of transitions. Band-to-tail transitions, the recombination of holes localized at acceptor-like states of the valence band's tail with free electrons from the conduction band. And free-to-bound transition, the recombination of free electrons with holes localized at acceptors which are deeper than the mean energy depth of potential fluctuations. The energy levels of these acceptors are affected by the valence band tails. The characteristic feature of the such bands is broad and asymmetrical shape, a centrifugal energy shift with excitation intensity rising. In our case, 3 main bands shift to the higher energy with the excitation intensity rising. And the high rates of such blue shifts suggest a band-tail rarity mechanism of the radiative recombinations for the 3 main peaks, whereas the 4th peak and the 5 peaks are more likely related to the free-to-bound recombination of free electrons with the holes localized at deep acceptors. Increasing excitation power raises the concentration of the holes which fill higher energy states in the band tail, so the energy between the conduction band and that of hole increase blue shifting the first, second, and third bands. Normalized spectra before and after radiation are shown on this slide. And to evaluate the changes, all photoluminescent spectra were divided into separate bands. Such decomposition allows not only to subtract one band from another, but also to estimate their shape. And the shape of the photoluminescence band associated with the valence band tail can be accurately fitted with the double sigmoidal function. Dominant band that we see at maximum excitation power almost disappears at 10 milliwatts. Such decomposition also allows us to estimate changes in the intensity of each photoluminescence band. Here you can see the power coefficients measured a slope of the intensity dependencies. And in conclusions, I'd like to say that irradiation reviews the photoluminescent intensity of the dominant bands, and we assign such a reduction with the formation of nodal radiation defects acting as deep troughs. Irradiation did not change the energy shift of the third band, suggesting that acceptor associated with this band was not affected by irradiation. However, irradiation reduced the energy shift of the second band from 13 millielectron volts per decade to 4 millielectron volts per decade, demonstrating a significant reduction of the compensation level associated with this acceptor. Warming to the room temperature doubles the intensity of the dominant band, probably due to the annealing of some radiation-induced defects. It increased the energy shift of the second peak to 10 millielectron volts per decade, demonstrated rising compensation level associated with this acceptor. And thank you for your attention.